This time we will discuss doubly reinforced beam. What is doubly reinforced beam? It is a beam which has reinforcement in two ways. One is in the tension zone, one is in the compression zone. So double reinforcement. And now, before starting the details, let us go start with very fundamentals. So this is a very simply supported beam. It has some load. If we take a cross section and it is something like this here, there's reinforcement here and there will be compression here. If this is our neutral axis and it is equivalent stress block, and this depth is A. So in this profile, to be in equilibrium, the compression must be equal to tension. We know that. Okay, so or I can write tension equals compression. So how can we find the compression? Stress times the area. Area is A times the B here. Okay, before starting here, I missed a point, which that is when doubly reinforced beam occurs. The answer is when there is a size restriction that this B and this ACE is recommended or forced, and your load is huge. In that time, doubly reinforced beam occurs. Otherwise, if nobody tells you this B and ACE, and you have full freedom to choose your B and ACE, then there will be no doubly reinforced beam. So if I forget this point, so I'm telling it earlier. So whenever you solve a problem, beam design problem, if the size is given, be careful. Now, other thing, if size is given, it must not be a doubly reinforced beam. It depends on load also. Size given, size is very small, but the load is huge. Then you need double reinforcement. Reinforcement in tension side, reinforcement in compression side. Okay, then come to this our business. Now for this case, tension equals compression. Now what happens if my size is now restricted, that I cannot exceed this B, I cannot exceed this ACE. But if my load is huge, what will happen? I need more strength. What can I do? I can simply add some reinforcement here that will give me some more tensile strength. That means, say this reinforcement is AS2 and my previous reinforcement was AS1. That means this is AS1. Then I am adding more reinforcement, which is AS2. Then my tension is increasing. Tensile capacity of this beam is increasing. But I need to balance this. If I need to balance this, I need to add some strength in my compression. Now I cannot add my concrete. If I can add my concrete, then my life is solved. My life will become easy. Problem is solved. But I cannot because of the size restriction. If there is size restriction, what can I do? I can add a reinforcement which is very equivalent to this reinforcement here. This reinforcement, we name it AS prime. Now this AS2 and AS prime, they are equivalent. They will give you equivalent force, but their amount or the area may not be same. Their amount, I'm going there, yes, but this AS prime and AS2 may be equal, may not be equal, but they must carry equal amount of force to balance it. So then if I am add some force, what is that force? AS prime area times my stress. So what I am doing now, I am adding something here, AS prime FS with my original C and with my, then I missed. So my total T is this, total C is this. Say this, I should not write this way actually. As I am changing, so my total T become now with this. The total C will be my previous one. Previous one was 85 A prime C AB plus, I am adding more here. This distance I had it previously. Now these two will be equal. Now again the discussion is about whether AS prime and AS2 equal or no. It is not. It may be equal when you can see here AS dash FS prime AS2 FY. If this stress, this FS means stress here, stress here. If my stress here, this stress becomes Fy, then these two will be equal. Then their amount will be equal. Okay, so before before going to something else, my design equation, let us discuss here. When I will use Fs prime, when I will use Fy. It also depends on Fy means yield. This is any other stress. We should say that if this reinforcement yields, then stress is Fy. If this reinforcement doesn't yield, then it is Fs prime. Now, how do I know? We have to find the strain here. Strain. We need to find strain here. If this strain is more than my yield strain, then it yields. If that strain is less than my yield strain, then it doesn't. How to find this? Okay, if I draw the strain diagram, okay, say here, if we draw the strain diagram, say this is my, oh, by the way, this distance we call is D prime. And this is A, and this should be somewhere, this should be C. So if I draw the strain diagram is like this, so this portion will be C, and this portion is D prime, and the strain here is 0.003 because it is concrete. I am looking for strain here, epsilon S here. How to find this? Just take this similar, I do not need A, so delete this to make simple. So I am dividing epsilon S prime divided by 003 using similar angle triangle. So this divided by this equals this divided by whole. So what is this portion? This portion is C minus D prime divided by whole C. So epsilon S is D minus C prime by C 0.00C. So using this equation, you can find the strain in this steel. Now if this strain yields more than yield, then your stress here is yield stress. Okay, what is my yield strain? So yield strain is epsilon y is Fy divided by E. You saw this equation in your strength of material class in this format. Strain is stress divided by modulus. In this subject or in this reinforced concrete design class, we do not use sigma for stress, we use lowercase a. Okay. Okay, now you know that E is 29,000 KSI for any steel. If it is 60 grade steel, Fy is 60 KSI. If your steel is 40 KSI, 40 grade steel, Fy is 40 KSI. So you can calculate this. Then you can compare. If this is less than this, then your stress here is Fs. If this value is greater than this, that means if epsilon prime is greater or equal than Ey, then your Fs prime is Fy. So that is how to find whether this steel will yield or no. Simply find the strain there. Once you find the strain there, compare it with yield strength and then find it. So that discussion is done. Next discussion is the design equation. Okay, so let me try a new figure. So doubly reinforced beam, there will be reinforcement here, and I need to add more reinforcements here. This reinforcement is here. This is AS prime. This is AS2, and color it. This is AS1. So this will be this plus or okay. So this is my double reinforcement beam. What can I do? I can split this reinforcement into like separate beam. So this beam is actually summation of this and this. Here is my rectangular beam. This is my double. The combination is steel and equivalent is steel. So for this, if I take the moment here, I will get AS1 Fy d A minus over 2. So this portion is my A. My stress here will be, if I take moment here, it will be AS2 Fy. Oh, I forgot to tell you that this distance is obviously D, whatever we know. This distance is D, this distance is D prime. Okay, so if I take moment here, AS2 Fy d minus D dash. If I take moment here, my equation will be AS prime, Fs prime, because here my stress I do not know, D minus D dash. Here, if I take moment here, I will get this moment. If I take moment here, for this I will get moment F prime C A B D A minus 2. We know this equation. So this equation is very popular. You know that we use this equation to find the moment capacity. We can use this equation also, no problem. These two are equal, these two are equal. If I take moment here, I'll get this one. If I take moment here, I'll get this one. For this case, if I take moment here, I'll get this equation. If I take moment here, I'll get this equation. So both are equal. Any one should be good. But these two, I mostly use these two equation. The reason is this is very simple to me because it is all about this reinforcement. So my total capacity will be the sum of this. So my nominal strength capacity equal this plus this. Then my factored or design or ultimate EMU will be, if I add a phi here, is on Fy d A minus 2 plus phi here is 2 Fy d minus d prime. So this is the design capacity of a doubly reinforced beam. Even in your homework or in your exam, if you know the reinforcement, you can easily find the moment capacity. Now in this portion, if you want to use this reinforcement, no problem. For this portion, you can write this one also. S prime Fs prime d minus d dash. This portion you can also use this equation, no problem. But only problem is if you want to use this equation, you have to find Fs prime. How to find Fs prime? I just discussed. Okay, To find fs prime, you have to find your a, you have to find your beta 1, then c, then epsilon s prime, compare it with your yield strength, compare it. If this is equal or greater than this is yield stress fy. If this value is less than this, it is not yielding. So then how to find this? Oh, maybe that time I did not tell you. Okay, write it down clearly. If epsilon s prime greater or equal to f epsilon y, then your yield stress is fy. If your strain is less than yield strain, how to find fs prime? Simple. This equation. If your stress is less than yield, that means it is not yielding. Your stress will be strain times modulus. So just do this, then you will find this. So you can use this portion or this portion, whatever you like. So I will summarize again. So doubly reinforced beam occurs when there is a size restriction and my load is huge, both. If there is no size restriction, then there will be no question of doubly reinforced beam. And something else is also that this reinforcement and this reinforcement may be equal, may not be equal. If this reinforcement yields, then they will be equal, because you can see if it yields, then it is fy, and if this will be the same thing, as prime and as2 will be same. If it doesn't yield, then this reinforcement will be higher. Okay, so I will wrap up. In the next video I will discuss the design steps of doubly reinforcement beam, and soon after then I will discuss some examples. Thank you.